something vast is moving beneath our feet. For decades, Bigfoot reports have painted a familiar picture, a shape slipping through old growth, snapped saplings, enormous prints in the mud, a shadow along a riverbank at dusk. Those surface traces are real, but what if they are only the visible tips of a far more organized phenomenon? What if Bigfoot is not merely a loner wandering the woods, but part of an intentional, continent-spanning system of hidden routes, channels that run out of sight through caves, lava tubes, abandoned mines, culverts, and underground streams? Tonight, I will show you the underground theory. We will walk the hidden corridors these witnesses point to, lay out the evidence that leads under the canopy, and explore the startling implications for every eyewitness account ever written off as folklore. This is not idle speculation. The case I'll present is built from layered sources: eyewitness testimony from miners, spelunkers, and rangers, historical and ethnographic records, geophysical anomalies flagged by engineers, and leaked documents that suggest official interest in subterranean voids where creatures might travel. By the end of this presentation, you will know 3 unsettling things. First, where Bigfoot's hidden migration routes are most likely concentrated, the geological and man-made landscapes that create continuous underground passages. Second, what clear signs indicate an active subterranean corridor, thermal pulses inside caves, chest-height gouges, and arranged stone markers at junctions, fresh prints in cave mouths, and low-frequency acoustic patterns that precede surface sightings. Third, what responsible actions officials and civilians must take to confirm or avoid these corridors, the non-invasive methods that can verify movement without endangering people or destroying potential habitat. Imagine following a faint line on the forest floor that doesn't end at a feeding ground but at an entrance hidden beneath a collapsed boulder, a rusted mine portal, or a culvert under a highway. Picture hearing echoes that are not wind but the beat of a heavy biped moving through a tunnel. Consider that investigators searching the treetops may have missed the primary highways these creatures use because those highways are underground. This matters. If these corridors exist and are used regularly, they function as ecological highways, routes that shelter Bigfoot from hunters, surveillance, and weather while allowing them to travel long distances, move young, and gather in protected junctions. Exposing them carries responsibility. The information here is meant to guide research and safety, not to encourage reckless intrusion. Patterns repeat, evidence accumulates, and the places people rarely look are where answers now dwell. Stay with me. Over the next 7 segments, we will move from the first hints of subterranean movement to concrete data, thermal and acoustic anomalies, field reports from miners and Forest Service personnel, mapping evidence, and finally, the exact markers and precautions that reveal these hidden migration routes. By the end, you'll understand why many sightings have defied conventional explanation and where to look, safely and methodically, if you want to. Find the shadowed tracings of Bigfoot's secret highways. This is a guided reveal. The truth hidden beneath our roads and rivers is not just possible, it is increasingly plausible. The next step is to open our eyes to what we have been walking over all along. To treat the underground theory as anything more than a wild idea, we have to anchor it in people and data we can trust, the kind of witnesses and records that force a question mark into the mouths of skeptics. Over the last 2 decades, a surprising and stubborn thread has appeared. Retired spelunkers, miners who spent nights underground, Forest Service rangers, field biologists, and even a handful of whistleblowers from mapping projects, all reporting anomalies that point below the surface. Start with the biology. Dr. Laura Helms, a mammalian ecologist who analyzed hundreds of anomalous hair samples, wrote in a private report that a subset of specimens showed traits you'd expect from creatures that spend serious time in low-light environments. The hairs had unusual keratin density, microabrasions, and wear patterns inconsistent with animals that live exclusively in trees or open forest. Dr. Helms stopped short of a dramatic label, but her words are quiet and sharp. The biology we measured aligns with animals adapted to subterranean or at least semi-subterranean life. Then there are the field witnesses. Tom Eddings, a retired U.S. Forest Service ranger, is a careful man who logged the odd and the ordinary for 30 years. He kept records of trails that ended at sinkholes and collapsed stream passages, repeatedly finding deep drag marks and scrape patterns around culvert mouths after storms. Those traces aren't random. They cluster where water meets collapsed ground. Miguel Alvarez, a retired coal miner, recalls a night shift decades ago when he saw enormous impressions pressed into a tunnel, floor footprints too large to be bare, spaced with a wide, deliberate stride. His account mirrors other miners' reports from the Appalachians, where old workings intersect natural karst. Technical evidence nudges these stories toward the plausible, a declassified portion of a state transportation. Mapping project revealed anomalous voids and tunnel-like channels beneath river valleys and highway easements in parts of the Pacific Northwest. Engineers initially labeled them geologic irregularities, but several geologists flagged a more organized pattern. Interconnected cavities consistent with karst drainage and legacy mining that line up in ways unlikely to be coincidence. When old mine maps overlay with modern sighting clusters, the coincidences become a pattern. Indigenous oral histories add another layer. Tribes of the Pacific Northwest have long told of large beings that travel the hidden ways and reappear at seasonal markers. These stories, written off as myth by some, match geography in precise ways. Lava tubes near salmon runs, cave systems linked to ancient river channels. When those oral routes are drawn on maps, they echo the same corridors where modern sightings concentrate. Finally, independent researchers using thermal drones, low-frequency acoustic arrays, and ground-penetrating radar have recorded persistent anomalies coming from below-ground heat signatures that move into cave mouths. Slow, heavy impacts consistent with a bipedal weight, acoustic patterns that precede surface sightings by 1 to 3 days. In several documented cases, teams who followed those signals to culverts or cave openings found fresh prints, scat-like matter, and organized piles of debris that didn't belong to local wildlife. Taken together, these strands form a web rather than a single thread. None of the sources alone is an earth-shaking admission. Together, they become harder to dismiss. Skeptics will point to coincidence, to confirmation bias, to folklore. But convergence matters. Biologists noting subterranean adaptations, miners and rangers finding repeatable traces, engineers mapping hidden voids, indigenous accounts describing hidden ways, and sensors recording below-ground movement all converging on the same places. That convergence is the crucial context. It reframes scattered anecdotes into a plausible model, corridors beneath our feet that connect distant habitats, offering shelter and routes for movement. The underground theory doesn't end the mystery. It gives a new map, one that demands careful, responsible investigation. Before we lay the map of routes, pause with me and look at the small, strange things that pushed investigators toward the underground theory. These aren't headline sightings or blurred photos. They are the subtle, repeatable clues that, when stacked together, change the way you see a forest floor or a cave mouth. They are the puzzle pieces found long before anyone imagined a continent-spanning subterranean highway, and they demand that we take the underground seriously. Start with heat. Thermal imaging has become a standard tool for modern fieldwork, and it tells a different story than the eye. In at least 3 independent cases across the Cascades and the Appalachians, teams recorded moving warm masses, entering cave or tube mouths, and vanishing beneath the surface. One striking instance, a thermal drone hovered over a collapsed lava tube at dusk and tracked a 10-minute slow-moving heat signature that entered the tube mouth and never re-emerged within the camera's range. Locals later reported heavy stomps and a guttural, echoing call that night. These pulses are too localized and too behaviorally regular to be random geothermal blips. They move, stop, and resume as if guided. Then there are the traces left in the dark places themselves. Speleologists and retired miners started sending field notes that read like a different language. Hair clumps that failed to match regional felids or bears, huge foot casts pressed into soft clay, and scratch marks in passage walls scratched at chest height. One spelunker described broad, parallel gouges in a narrow tunnel, not the single clawed scrape you'd expect from a bear clawing at rock, but even repeated scars that line a path where a tall, upright body is squeezed through room after room. In several caves, investigators found what I'll call waymarks. Carefully arranged piles of stones or stacked branches in junctions and bins. They're not haphazard. Their placement repeats across unconnected sites, suggesting someone or something is marking a route. The acoustics are equally odd. Low-frequency recorders placed in caves and mine shafts have captured slow, deliberate thumps and long, low calls that reverberate for minutes. These are not bird or bat noises, nor are they typical mammalian chatter. The recorded waveforms show a heavy bipedal gait, prolonged impacts, spaced in a cadence that matches eyewitness descriptions of a wide stride. In several documented sequences, those subterranean sounds preceded surface sightings by 1 to 3 days, implying movement from inner passages to the outside world and back again. That timing matters. It suggests the underground is not static shelter but a mobile corridor, used in predictable rhythms. Archaeology, not the humankind, but the artifacts left behind, adds another layer. On disused logging roads and near old culverts, investigators cataloged enormous footprints in low-made branches, arranged like simple signposts, and clumps of bones methodically placed at key junctions. In one site, fish bones were laid out in a semicircle at the entrance of a culvert, a pattern that turned up, with variations, dozens of miles away. These caches don't appear to be feeding piles scavenged by local mammals. They bear signs of deliberation. The repetition of motif across distant, unconnected locations hints at some shared convention, a rudimentary system of communication or navigation. Maps, too, began to speak. When researchers overlaid historical mine charts, lava tube surveys, and karst drainage maps with decades of sighting records, a startling correlation emerged. Sighting clusters track the skeleton of underground networks where old mines intersect solution caves, where rivers cut through seibel bedrock, where lava flows puncture the surface with tube mouths. The coincidence is not occasional, it is systemic. In regions where natural and man-made voids align, sightings concentrate, and the pattern holds across mountain ranges and climatic zones. Finally, there are the hints of official attention. A handful of FOIA releases and internal memos show state and local agencies quietly flagging unclassified anomalies. Near culverts and sinkholes, notes recommending soil sampling in cave mouths and temporary monitoring of drainage systems. They do not leap to sensational conclusions, but they do confirm that professionals have noticed the same odd overlaps we're describing. Engineers, geologists, and wildlife managers have, at times, crossed paths over the same strange traces and come away with questions. Taken together, these threads prime the mind for a radical possibility. Heat signals, physical traces, low-frequency soundscapes, repeated artifact motifs, cartographic overlaps, and cautious official interest all point below the canopy. Each piece alone can be rationalized. Stacked, they form a pattern that demands explanation. The underground is not an incidental refuge, it's a working system of movement and markers, a network that can hide scale and intention from casual observation. Hold on to that. In the next section, we will assemble these pieces into the central revelation, how these corridors are structured, where they concentrate, and why they explain the quirks that have confounded investigators for generations. What the pieces we've gathered point to is not a handful of isolated caves, but a multi-tiered functioning network, natural and man-made passages stitched together into repeatable routes a large, intelligent biped could use to travel, hide, and meet. Think of it as an underground highway system with entry ramps, junctions, and rest stops. Only the cars are large animals that prefer to move out of sight. The first part of the revelation is simple and concrete. The corridors are real types of passages. They connect in predictable ways, and they concentrate where geology and human history overlap. There are 5 corridor types that show up again and again in the records. First, karst and solution caves, where limestone and other soluble rocks dominate. Water carves complex mazes of sinkholes, delines, and passages. These systems often drain whole watersheds and reappear as springs. For an animal that needs water but avoids exposure, following an underground river is the perfect strategy. In regions with extensive karst, sighting clusters line up almost exactly with mapped cave networks and spring outlets. Second, lava tubes and basalt caverns. In volcanic country, long dry tubes form when the top of a lava flow cools and the molten interior drains away. These tubes can run for miles and stay relatively stable. The Pacific Northwest's volcanic fields, parts of Oregon, Idaho, and Washington contain networks of these tubes that sit under dense forest. In several cases, thermal and eyewitness reports center on tube mouths or collapse zones. Third, abandoned mines and prospecting tunnels. Mining created artificial corridors across Appalachia, the Rockies, and the West. Old adits, horizontal shafts and galleries, when they intersect natural voids or water tables, can extend travel options and provide easy concealed entrances near roads and old settlements. Miners' accounts from multiple regions describe enormous impressions and unexplained movement inside shafts, the kind of testimony that becomes more plausible when those shafts connect to larger cave systems. Fourth, culverts, storm drains, and decayed highway conduits. These man-made channels are often the weak link between surface and depth. Large, collapsed culverts or box drains commonly open into bigger voids or dead-end into sinkholes. For an animal using hidden routes, culverts are convenient. Low-profile access points that skirt human traffic while leading to deeper passages. Fifth, subterranean riparian corridors, underground streams, and saturated passages that carry water and air. These are the corridors that link drinking sources, and they often surface at springs or seeps. The convergence of water, shelter, and navigation makes them prime travel lanes. How these corridor types connect is crucial. Junctions occur where a lava tube drops into a karst sink, where a mine adit cuts into a natural cavern, or where a culvert feeds into a collapsed passage. At these intersections, you find repeated signs, piles of stones, bone clusters, scratch marks, and fresh prints. These are not random leftovers. They function like trail signs and rest stops. We call them way stations, recurring nodes in the network that mark direction, resources, or safe places to pause. Researchers have found identical marker motifs, stacked stones, arranged branches, bone placements at unconnected sites within the same mapped corridor. That repetition suggests a shared system of navigation, not mere coincidence. Surface linkages explain the puzzling pattern of sightings. In many places, corridors rise close to ridgelines or shallow soils. The creatures slip onto the surface to feed, socialize, or move between short stretches, then return underground. This pattern explains clusters of daytime ridge sightings followed by sudden nocturnal silence. It explains why tracks appear miles from expected habitat and why a tracking line sometimes ends at a culvert mouth or a sinkhole, rather than continuing across open ground. The corridors concentrate where three maps overlap: geology, hydrology, and human disturbance, where karst or lava fields intersect rivers and old mining districts. The skeleton of an underground network emerges. Notable hot zones include the Cascades and Columbia Basin, where lava tubes and river canyons cross, the northern Rockies in Idaho, with fractured basalt and karst, and the Appalachians and Ozarks, where extensive cave systems and abandoned mines create miles-long, hidden passages. Even arid plateaus and desert margins show corridors where deep washes, cave systems, and old prospecting tunnels meet, explaining sightings in places people assume are inhospitable. There are recognizable structural features investigators can look for without breaking rules or risking safety. Fresh, large tracks pressed in soft loam at cave mouths. Deep, parallel gouges on passage walls, and pollarded saplings near sinkholes. Deliberate piles of stones or bone caches concentrated at junctions. Thermal pulses moving through a tube captured on thermal imaging at night. Low-frequency acoustic patterns and cave passages that match the cadence of a heavy biped. When these signs cluster within mapped cave or mine networks, they change a theory into a working model. This model reframes old mysteries. Footprints that appeared to start or stop abruptly make sense when you realize the line crossed an underground aperture. Seasonal sighting pulses align with routes that connect spawning rivers, berry slopes, and high ridges. Impromptu gatherings or multiple individual sightings fit a pattern where way stations and junctions serve as rendezvous points, protected spaces for birthing, social exchange, or movement planning. This is not an accidental scatter of anecdotes. It's an infrastructural explanation. Corridors that allow an animal to travel long distances with relative safety and little surface trace. The map of sightings, when read against cave surveys, mine maps, and river drainages, becomes legible. The next part will show how these routes are used in practice, the behaviors that maintain them, the seasonal rhythms they follow, and the concrete steps scientists and citizens can take to verify or avoid them. Now that the corridors have a shape on the map, the picture of how they're used becomes startlingly precise. These are not random holes in the ground. They are a working system with rhythm, purpose, and rules. Understanding that behavior changes everything: how we search, how we protect, and how we keep people safe. Seasonal migration is the backbone of the system. Groups move on a timetable tied to food, water, and breeding. In salmon country, subterranean routes lead from river springs up into interior ridges in late summer and fall, allowing groups to feed and then retreat to sheltered junctions before winter storms. In berry country, the same pattern repeats on a shorter cycle: surface feeding sessions at dawn and dusk, then return to deep junctions during the day where juveniles and older animals stay hidden. These movements explain why sightings spike in narrow seasonal windows and why a string of sightings may suddenly stop at a particular ridge, the line crossed an entrance to a deeper highway. Reproductive rendezvous and nursery sites are another key use. The way stations we describe, piles of stones, bone caches, and marked passage walls appear to function like protected rooms. Eyewitness reports consistently describe multiple large individuals entering cave mouths and weeks later returning with smaller, younger animals. These junctions offer stable temperatures, freshwater seeps, and complex side passages that protect young from predators and human disturbance. If childbirth or rearing occurs underground, it would explain the extreme caution and secrecy observers report when groups are nearby. Avoidance and stealth are practical advantages. Moving beneath the surface removes the continuous scent and visual traces animals leave above ground. A corridor system allows long-distance relocation without leaving a single, followable trail across the forest. That explains why trackers sometimes lose an animal midstream. There is no surface line left to follow because the animal slipped into a culvert, a collapsed shaft, or a lava tube. Finally, the material signs that arrange stones. Bone clusters, parallel gouges read, like a crude but effective communication network. These markers show pattern and repetition across vast distances, suggesting that root knowledge is learned and passed along. Whether cultural or instinctual, these signs reduce navigational errors and likely warn groups away from active human presence. They resemble trail markers in human terms. A quick read at a junction tells a traveling group whether a path is safe, when it was last used, and which branch leads toward water or highland feeding zones. From this behavioral model come concrete, responsible steps for officials and researchers. The goal is verification without harm and invasive science that records presence and pattern while protecting people and the animals themselves. First, coordinated subterranean monitoring. static thermal camera arrays, and low-frequency acoustic sensors positioned at likely mouths, culverts beneath highways. Lava tube entrances, sinkholes give the strongest return for effort. Thermal arrays can detect the short-lived, warm pulses we described. Low-frequency microphones pick up the slow, heavy cadence of a biped moving in confined stone, sounds that travel far underground. The sensors should run continuously for several weeks in target seasons to capture temporal patterns. Second, environmental DNA eDNA sampling. Collecting water and soil samples from springs, seeps, and cave puddles is a non-invasive way to detect large mammals. Properly handled, eDNA can reveal a species' mitochondrial footprints without a single disturbance. Labs must follow Chenov custody and contamination protocols, and results should be compared across sites to build a region-wide picture. Third, geophysical imaging. Ground-penetrating radar and targeted borehole surveys help identify voids and junction sizes. Combined with historical mind maps, GPR can pinpoint where natural and artificial passages intersect. This narrows search areas and reduces unnecessary human entry into unstable spaces. Fourth, legal protective protocols. Any investigation that approaches potential corridors must involve landowners, land managers, and permitting authorities. Abandoned mines and caves are physically dangerous and may also intersect sensitive habitats. Coordinating with agencies prevents accidental destruction of corridors and minimizes the risk of human injury. These methods already have supporting testimony. Spelunker. Daniel Price heard 3 heavy steps pass inside a lava tube and, days later, returned to find enormous fresh impressions and a stone pile at a junction identical to a stone pile cataloged 30 miles away. A highway crew in Oregon found deep gouges and fish bones at a culvert mouth, then recorded a warm body slipping into the pipe after dusk on a handheld thermal sweep. A miner in Kentucky described a line of wide-stride footprints across a horizontal shaft and a low guttural call. The shaft later collapsed, hiding what may have been a junction into deeper karst passages. These are not isolated tales. They repeat in different forms across landscapes and decades. But there are urgent warnings. Do not enter unknown caves or mines alone. Structural collapse, toxic gases, and hypothermia are real hazards. Chasing sightings in confined spaces endangers both people and animals. Disturbing way stations, removing stones or bone piles, could break a communication system and provoke unknown reactions. If you find fresh signs, document from a distance, record timestamps, and contact professionals. The solution is a method, not a trophy. Find likely mouths on maps, monitor non-invasively, collect eDNA with scientific partners, use GPR to narrow targets. Involve land managers before any entry. That process gives us a way to learn without destroying what we seek. If Bigfoot uses these corridors, they are a resilient adaptation, one that has allowed movement, breeding, and cultural transmission under the radar of conventional study. Our response must be careful, collaborative, and scientifically rigorous. Only then can we move from story to evidence, from rumor to record, without risking lives or severing the very roots that have carried these animals for generations. If you want to put the underground theory to the test, or at least document what you see without putting yourself or others at risk, there is a simple, repeatable playbook. This is not about heroics. It's about careful observation, good science, and restraint. Follow these steps and you will turn rumor into usable data while protecting people, land, and any animals that might be using these routes. 1. Read the land before you go. Start at home with maps. Look for overlap. Old mine claim maps, karst limestone layers, lava flow fields, river drainages, and culvert networks. Free online geological maps, county mine archives, and topo maps reveal likely corridor mouths, collapsed sinkholes, large culvert outlets, lava tube openings near ridgelines, and abandoned adits next to springs. Mark these as areas of interest, not precise targets to publish, but places to monitor. To build a low-risk monitoring kit, you don't need to break the bank. A decent thermal monocular or an inexpensive smartphone thermal attachment will show moving warm masses at a distance. A pair of binoculars, a high-resolution camera with zoom, and a tripod are essential. Add a long-duration audio recorder capable of capturing low-frequency sound. Devices used by bat researchers or wildlife recorders work well. Include a headlamp, spare batteries, a GPS unit or phone with offline mapping, and basic first aid supplies. If you plan to sample, bring sterile gloves, sealed sample tubes, and a cooler, but only collect eDNA samples in partnership with a lab or university. 3. Observe from a safe distance. Systematically don't approach entrances. Set up at a vantage point where you can see culvert aprons, sinkhole rims, or cave mouths without walking into unstable ground. Use thermal imaging and binoculars to scan at dusk and before dawn common windows of movement. Record continuous audio overnight when possible. Keep a log, date, time, weather, moon phase, camera settings. An exact vantage point note nearby public landmark rather than GPS coordinates if you intend to share publicly. For document correctly, photos and audio are only useful if they're precise. Include scale in every photograph, a stick or a hand. Labeled, take shots from multiple angles, and timestamp everything. Forward tracks found on the surface, photograph before touching. If you must make a plaster cast, do so only with permission from landowners and after checking local regulations and document chain of custody. For eDNA, collect water or soil samples using sterile technique and ship them to a lab with experience in low concentration mammal markers. Metadata matters: location, depth, water flow, recent weather. 5. Use non-invasive technology. First, thermal sweeps, long-duration acoustic recorders, remote camera traps set at a distance, and environmental sampling are the priority tools. Ground-penetrating radar and borehole surveys are powerful, but require professional operators and permission. If a site consistently shows thermal pulses or acoustic signatures, that's the time to involve trained geophysicists or cave scientists rather than going deeper yourself. 6. Safety and legal protocol. Never enter an abandoned mine or an unknown cave alone. Even experienced cavers carry gas detectors, helmets, ropes, and a support team. Mines collapse, pockets of bad air can be fatal, and hypothermia sets in fast underground. Respect private property. Get written permission from landowners. If you find clear, fresh signs, large tracks, bone piles, organized markers, document from a distance and notify land managers or a university lab. Don't publicize exact coordinates that invites trespass, vandalism, or harm to wildlife. 7. Partner with credible organizations. Contact local university biology or geology departments, regional spelunking clubs, reputable wildlife labs, or established cryptid research groups with professional ties. They can run eDNA tests, arrange GPR or thermal surveys, and provide study design that stands up to peer review. Sharing anonymized data, date, general area, environmental conditions, and media helps build a pattern without exposing sites to exploitation. 8. What to do if you encounter activity. If you see a large, warm body move into an entrance or hear low-frequency knocks or calls, retreat calmly. Do not pursue into a confined space. Record direction, time, and any distinguishing sounds or marks. Give the area time. Many accounts report animals returning to the surface hours or days later. The priority is safety and documentation, not confrontation. 9. Respect the markers. If you find arranged stones, bone clusters, or scratch marks, photograph them and leave them intact. These may be navigational aids, social signals, or culturally significant features for an intelligent animal. Tampering could both destroy evidence and provoke unknown responses. 10. Report in a standard format. Use a simple incident form: date, time, general location, county, nearest public landmark, environmental conditions, equipment used, media files, and a short narrative. Keep copies and share with trusted professionals. Local land managers and wildlife authorities should be alerted if evidence suggests repeated corridor use. This approach turns curiosity into a methodology. It gives you tools to collect reproducible data while minimizing harm. Above all, it recognizes two truths we have uncovered: the corridors are fragile, and the creatures that use them, if they exist, are both elusive and potentially vulnerable to human disruption. Proceed with patience, process, and respect. The underground will not be revealed by rashness, but by steady, careful listening, and by teams that know how to read what the land quietly leaves behind. We started with a single, unsettling thought. What if the most convincing traces of Bigfoot are not left in the open, but beneath our feet? Over the last 6 segments, we threaded together testimony from spelunkers and miners, thermal and acoustic anomalies, declassified maps, indigenous oral histories, and field evidence that refuses easy explanation. Those threads converge on one hard idea: an organized system of subterranean corridors, natural caves, lava tubes, abandoned mines, culverts, and underground streams that function as travel routes, staging grounds, and nurseries for a large, intelligent, mobile population. This conclusion changes everything about how we understand sightings. Clusters of reports along ridgelines, the sudden vanishing of animals that seem to be tracked for miles, and the recurring pattern of chest-high gouges, arranged stones, and bone caches all make sense when read as signs along a hidden highway. Thermal pulses passing into tube mouths, low-frequency footsteps echoed in cavern galleries, and eDNA hints from spring waters are not disparate curiosities. They are the signals of motion on a map that humans rarely see. The implications are immediate and weighty. First, if these corridors are real and used regularly, they are fragile infrastructure, development, poorly managed mining, roadwork that ignores karst, and the curiosity of the public could break connections that populations depend on. Second, approaching these places without training risks lives. Abandoned shafts collapse, pockets of bad air can kill. And confronting an unknown intelligent animal in a confined tunnel invites unpredictable danger for both parties. Third, this is not merely a hunt for spectacle. It is a call to systematic, careful science. Here's what must happen next in 3 practical and ethical moves. 1. Observe and document, but do not intrude. From a safe distance, gather repeatable data, long-duration thermal recordings at likely entrances, low-frequency acoustic logs, high-resolution imagery of covert mouths, sinkholes, and lava tube openings. Note timing, weather, and behavior patterns. Use standardized incident reports that record date, general area, county, or public landmark, equipment used, and media files. Do not publicize exact coordinates. Sharing anonymized, consistent data helps scientists see patterns without inviting trespassers or vandals. To bring in the right partners. This is work for trained teams, geology departments, reputable spelunking clubs, wildlife labs, and conservation organizations have the tools and ethical frameworks to sample safely, GPR to map voids, eDNA to screen water and sediment, thermal arrays and acoustic networks to track movement over time. Coordinate with land managers and obtain permits. When civilians find potential markers, arrange stones, bone clusters, or fresh large tracks. Document and notify professionals rather than attempting to excavate or disturb them. 3. Protect and plan. If evidence supports repeated use of a corridor, land use managers should consider temporary access restrictions and environmental assessments before any development. Planners must treat karst and legacy mine intersections as sensitive zones. Conservation-minded policy can prevent inadvertent destruction of routes that may be critical for an intelligent animal's movement and survival. There are ethical decisions embedded here. If an intelligent species uses these passages to avoid humans, we have a responsibility not to force contact, revealing exact locations, risks, exploitation, harassment, and ecological harm. Our goal must be knowledge coupled with protection. Verify using non-invasive science, then use that knowledge to shield these corridors from harm. To the skeptic, this model explains a cluster of anomalies better than coincidence. To the believer, it gives a method to test claims without reckless bravery. To local authorities and scientists, it lays out clear, actionable steps that reduce risk while maximizing the chance of discovery. Finally, a word about motive and consequence. The corridor model explains not only movement, but behavior. Seasonal timing tied to food runs, protected nursery junctions, and a rudimentary sign system of stones and marks. It reframes Bigfoot from a lone forest phantom to a creature with infrastructure, and with infrastructure comes vulnerability. That vulnerability obliges caution. We have been looking up and outward while the traces pointed down. The underground highways we have outlined are dark and deliberate, running under rivers and roads, curling through lava flows and limestone, appearing where old maps and oral histories overlap. They wait for patient, careful listening. If you take anything from this, let it be this: observe from a distance, document with rigor, partner with professionals, and protect what you find. The truth may be underground, but how we handle it will determine whether that truth survives the light. What comes next is practical, immediate, and ethically anchored. A realistic plan for turning the underground theory from a compelling hypothesis into responsible action, without trampling fragile places or provoking reckless curiosity. First, establish focused pilot programs. Pick 3 regions where the corridor overlay is strongest: 1 lava tube-rich zone in the Pacific Northwest, 1 karst-heavy segment in the Appalachians or Ozarks, and 1 mixed legacy mine landscape in the interior West. Each pilot should be small, time-limited, and run by a coalition, a university geology or biology department, a trusted local conservation group, and representatives from nearby indigenous nations. Their charge is simple: verify corridor activity using only non-invasive, legally sanctioned methods, and document findings under strict ethical rules. What that looks like in practice: remote sensing arrays set at likely mouths, long-duration thermal cameras mounted out of sight, low-frequency audio recorders, and motion-triggered infrared units placed at a safe distance. These collect patterns without ever disturbing a site. eDNA sampling, coordinated through accredited labs. Take water and surface soil swabs only where permitted, with chain of custody protocols and community oversight. eDNA can detect the presence of large mammals without a single footstep into a cave. Geophysical surveys, conducted from public rights-of-ways, ground-penetrating radar and resistivity scans can reveal voids and junctions without forcing open access to unstable shafts. Where mines are involved, pair the imaging with historical maps to locate probable connections. Second, protect before you publish. Data sharing